I was like, where is it? California.
Well, welcome to the reconvening of Research on the Road live broadcasts. We'll be talking about biomimicry today. So we're focusing on how nature inspires engineering and what kind of have been used to develop products that we use every day. There's so many things that are just everyday objects to us that in the designing process relied on and were influenced by the structures that we see in nature, whether that be actual physical features or just chemical products. There's so many different ways that we could talk about this. So we're going to get a perspective from my marine biology perspective, from Michael's paleontology perspective, and from Daniel's herpetology perspective. So to kick it off, I'm going to talk about marine biomimicry. I've got a few examples. So I work with barnacles, and so the obvious choice for me would have been to do barnacle cement in the designing and synthetic adhesives. And so barnacles attach very tightly to just about everything that they can come into contact with. They're a little bit choosy with what they'll stick to, but once they stick, they are stuck. And that includes rocks or piers or living things. Like my barnacles are stuck to manatees and turtles, so you know that they take what they can get. But I decided to go a slightly different route here because I want to talk about a little bit more of the charismatic megafauna side of marine biology. I think as much as I like barnacles, people are not as interested in barnacles, unfortunately. So I'm focusing on sharks and octopus because I think those guys are fun. Here is my marine biomimicry presentation. On the left, we have a great white shark, and on the right, we have a Pacific giant octopus. And so we'll start with our sharks because shark scales are amazing. They're not like fish scales. They're actually called something completely different. They're called denticles because they are essentially teeth that cover their entire body. So if you've ever felt a shark, it feels kind of like sandpaper. And if you zoom in really closely on that, you'll see that it does not look like nice layered round scales like you would think of a scaling a freshwater fish or something if you've come across that in seafood. It's it's quite a sight. So shark skin has these V-shaped scales, denticles, and they really are. It's not that they're like teeth, not that they look like teeth. They are tooth structures. They're made of the same materials as their teeth are formed. They just are microscopic and coat their entire body. So you would think that having such rough skin would actually be a detriment to them in their speed of swimming, but it decreases drag and turbulence around the body of the shark and allows him to swim faster. So, and enhances thrust. So that is, if you were to zoom in on shark scales, those are your denticles. So you can see how they're kind of triangular tooth structures, and they're very hard and solid pieces at a microscopic level, of course. So you wouldn't cut your hand on it if you were to rub your hand across their body, but you can definitely feel the roughness of it. So a lot of industries have thought to use artificial shark skin, and for so many reasons, because the obvious would be to decrease drag. If it works for sharks, it could work for us. So Olympic swimsuit designers are always looking for the next way to make their swimmers faster and get an advantage in a competition set. And so they actually designed wetsuits that mimic these denticles and have the same structures and the same method of reducing drag and increasing thrust. And so Speedo even invented something called the fast skin fabric. And in their tests, even with Olympic swimmers, it could improve their speed by up to 4%, which doesn't sound like a lot, but when you're talking Olympic swimming speeds, 4% over your competitor is enough to win you a gold medal when it's that tight at the end of the race. And so in 2010, the Olympic governing body actually said no one can wear those because it gives you too much of an advantage. And if it's not an advantage across the board, that's an unfair advantage. So it's just back to your standard swimwear for the Olympic swimmers. Otherwise, they would be swimming actually too fast. So this is the Fast Skin from Speedo, and it doesn't, it doesn't actually have like shark scales on it like that. They designed it to look that way so that it would, kind of promote the vibe that they're going for with shark skin. But it has the same microscopic structures and the same methods that shark skin has. And so another way that they've used synthetic shark skin in biomimicry is to use it as a coating on the outside of shipping vessels and boats in general. And so like you see barnacles on living things, I mentioned that, and most of the large swimming species out in the ocean are bothered by barnacles at some point or other. And so they usually have methods of removal, and whether that's scraping against rocks or being able to have a symbiotic relationship with something that'll pick them off for them. But sharks don't have that problem at all. They actually don't stick to sharks. So anything really, algae, mussels, or barnacles don't stick to sharks. But they're a huge problem in the shipping industry because they produce a lot of drag. And when you're talking about a shipping vessel and you're talking about the cost that drag adds to the shipping and the amount of fuel costs and fuel emissions that is adding, you want it to be as efficient as possible. So they produced a shark skin coating, and it reduced biofouling on these vessels by up to 67%, which is huge. That increases the efficiency dramatically. And so they're hoping that they could use this for submarines and ships, or underwater robots, which would be cool. And there's actually shark paint, which would work not just for marine vessels and the sorts of things that we're running through water, because we're talking about the way that fluid is going across the surface, and drag works in any kind of fluid, which air qualifies for as well. So this shark skin paint is a coating of nanoparticles that actually reduces friction in air or water. So it would work in shipping vessels in the ocean, or it would work in airplanes as well. And so the claim, should it work out, is that if every airplane in the world were painted with it, we would reduce 4.48 million tons of fuel annually. And every ship, so not shipping industry as a whole, but each individual ship that would use this would save around 2,000 tons of fuel every year. So, and then another use, we're talking the climate change side here with our reduced fuel emissions, is also that it could benefit us by making more efficient wind turbines. So lots of good things there. And these coatings are actually antibacterial as well, the same ones that work for to prevent biofouling and algae development. And so they're talking about these as a surface covering to actually prevent transmission of microbes too. So places where microbial transmission occurs on surfaces could use this as the material coating to prevent those infections from spreading. So now we're going on to Octopus Skin. Our Octopus Skin is very well known for camouflage features, our chromatophores that can expand and contract and change the the overall appearance of the octopus as it moves through its environment. And so they've created a synthetic octopus skin that has these features, and it has heat sensitive dyes and light sensors. And this was developed by Harvard scientists. And so they created a soft color changing robot that was inspired by octopus and squid chromatophores. And it's got tiny channels that actually allow you to inject these dyes and move it through the surface so that you can mimic your surroundings and blend into the environment. Octopus Grip is also a focus. So these suction cups are very cool. They've made 3D printed suction cups, and they've used them for robots and mechanical uses, so that if something needs a stronger grip in an environment where humans can't be there, like cleaning up waste or something along those lines, something where they would need to collect but not put themselves in, put a person at harm. You can use these robots with the 3D printed octopus suction cups, and they're finger size, so they're about to scale with what you would expect, and they're made from a polymer that solidifies under UV light. And when they tested them, they were testing them in a military laboratory, and it was strong enough to hold up a soda bottle, which, I mean, you know, it's when you're talking about an arm full of these suction cups, each individual one being able to hold the weight of a filled bottle of soda is additive, and it makes a pretty impressive grip. So then last one, we've got wearable robotic arms, which they call supernumerary robotic limbs. And so you can mount them on, it's kind of like a backpack. I've got a video here. So it's shoulder mounted or mounted on the waist. And it can actually, you can control it with your own movements, but it increases the force and the strength of the arm. And also, of course, protects your own arm. So here's our video, quick video of an MIT laboratory testing it out. So not specifically octopus-like, except that it's very much reminiscent of the Spider-Man villain, Dr. Octopus. So that's kind of what we're going for there. And anytime you can increase the number of limbs, you kind of get that octopus vibe. So talking there about Spider-Man villains, we can kind of roll into Spider-Man and his adhesive properties with Daniel, because Daniel's talking about gecko feet. Daniel, you there?
Is it? Oh, okay.
Yeah.
What's up, everybody? Wild Man Dan here. How's it going, guys? So what I have today is I have a reptile. It's actually a gecko species. It's called the eyelash crested gecko, and these guys were found in Madagascar. They're also known as the New Caledonian gecko, because they were once thought to be extinct, and then poof, what do you know? We found them again. So did you guys know that geckos can actually climb up most surfaces, including glass? Now I have a little lizard here. Now this is my new bearded dragon. His name is Chulito. Now Chulito is not a bearded dragon. I mean, not a gecko. So if I put him on the glass, there's a pretty good chance that he will not actually stick onto it, unfortunately. And that's because he doesn't have the same type of toe pads that the gecko does. Even if they were bigger, like this one is Jubilee. As you can see, she fits on the entire glass here. She will just also slide right off. She's not capable of holding onto really smooth surfaces. Now, the gecko that I'm going to show you has an adaptation, which are those toe pads that we're talking about. This is a unique adaptation or a unique feature tool that this animal has in order to survive and thrive in its environment, which are usually up high in trees. Sometimes they can be found on walls, windows, especially if you go to any of your tropical areas, like let's say the Philippines, where they have the tokay gecko. You can find on most of the houses, there are tons of little geckos that are climbing and upside down, even on top of a ceiling. And the way they do that is absolutely incredible, and I'm going to show you guys right now. So let's go ahead and pull this guy out. Now, these guys are usually very quick jumpers. They're not as timid as the bearded dragon, unfortunately. So let's see if we can get him out without startling him too much. But here we have the eyelash crested gecko. And the reason why they're called the eyelash crested gecko is because they have those beautiful eyelashes there on the eyes. I hope you guys can see those, all right? Emily, if you give me a thumbs up if you guys can see those. You see the eye pretty well? All right, beautiful. So yeah, the eyelash crested gecko, and it gets that name because, and there we go. So this is what I was talking about. They like to jump a lot. So they have those beautiful eyelashes there on the eyes themselves. A really, really soft species. This guy is actually getting ready to shed. His skin is literally coming right off. And I'm going to show you guys right now how this guy literally holds on to even a smooth surface like glass. So let me just keep him there. So we've got him there on the glass. And now all I've got to do is just tilt it upright. And it looks like he's going to climb for a second. But if I keep tilting it,
cool.
What you'll notice is boom. There you go.
Whoa.
If you take a look there, you can see actually those toe pads that we're looking for right there. So those toe pads, they don't look like most lizard species legs or feet. These guys have little tiny hairs actually on their toe pads there. Tiny, tiny, tiny little hairs. And there's hundreds of thousands of millions of billions of them. And these tiny little hairs are called setae. If you're out there watching right now, I want you to go ahead and practice that word real quick, which is setae. Setae literally means just tiny, tiny hairs, except they're even smaller than, oh my goodness, this guy's ridiculous. They're even smaller than our tiny little hairs that we have on our face. There we go. I think we can make this work. So now, does it stop there? Is setae the smallest that we have when it comes to the gecko? No, it's not. It actually even gets smaller than that. And the only way we were able to figure that out is because of the electron microscope. And I think it was first discovered in Germany, as a matter of fact. Someone took the toe pads of the gecko and found out that it gets even tinier and tinier than the setae. And those are called spatulas. And yes, you heard me correct. Just like what you hear in the kitchen. Like you use a spatula, either your mom gets a wooden one to beat you over the head with, or you use it to cook in the house with, whatever it might be, it does look like a spatula. And because of the setae and the spatula, it increases surface area. Now, what that basically means is it gives it a lot more area to hold on to, even though it's so tiny, in order to support the body weight of this gecko. Because if you take a look, those little hands are super tiny compared to the rest of the body of the actual gecko itself. And as you can see, he's a really good jumper. So, but does all of those tiny little hairs and the spatulas and the setae really explain how the animal is able to hold on to something as smooth as the glass? And no, it doesn't. We had to do a little bit more research to figure out that it actually had to do with van der Waals forces. What this basically means is that those little setae and those spatulas are working together to create intermolecular attraction with the other molecules of the surface it's interacting with. So basically, the molecules of those spatula and setae are literally reacting with the molecules of whatever surface it's holding onto in order to cause an attraction, a force of attraction between those molecules. Absolutely incredible how this animal is able to utilize something so tiny and so small in order to hold on and thrive in the area which it lives in. Now, a way that we've been trying to mimic this little guy and many of the other species is with the Stanford Research Group. What they have done is they have developed a wall climbing grip that actually allows humans to hold on to a vertical surface with their entire body weight. Now, isn't that crazy? You could literally be a real-life Spider-Man, just like this beautiful gecko. So don't forget, geckos, not all species of geckos, but usually the ones that are arboreal. Now, that means that they're high up in the tree or they live above the ground. They will have these toe pads, which are filled with setae that get even smaller to the spatula level and that work with van der Waals forces to create an intermolecular attraction with whatever surface that they have. And don't forget, the other really cool part about guys, since they're arboreal, usually most gecko species have a oh man, I forgot what it's called. What is that called?
Prehensile.
Thank you. I was thinking so many other words. A prehensile tail, which basically means that they can use that beautiful tail of theirs in order to hold on to things and make sure that they don't fall, just like chameleons and many other species of monkeys, so on and so forth. So really cool. Eyelash crested gecko, intermolecular forces, Van Waals, sea tang, all sorts of cool stuff. But just remember that the world is crazy cool. You can find all sorts of stuff in little creatures, even like the gecko.
Wow, how many of those do you have?
So this one is actually a friend of mine's. Her name is Jessica. She has a bunch of animals. I cut down quite a bit, but I used to have these guys before. Back in the day, I think I had 9 or 10 of them. They're an incredible species.
Wow.
Yeah, I absolutely love them. And I don't know if you guys can see, but literally this guy's skin is just peeling off. He's going to jump again. Let me see if I can grab a chunk here. There you go. Let's see. This piece just tore off. They don't really like to sit still, and they are nocturnal. So there we go. So you guys can see it's literally just peeling right off. And usually what they'll do is they'll eat all this stuff. Looks like I already. Oh, well.
They were developing a synthetic adhesive that was, they call it Gecko because it was Gecko CT inspired as well as muscle cement. So the actual chemical adhesive that muscles produce to stick to things, as well as the CT structures, and they were trying to use that for both wet and dry adhesive applications. And so one of the ideas that they had for it was as surgical sutures. And so I don't know where that development went or if it actually went into commercial production, but I thought that was a cool overlap between the two and in terms of biomimicry. So Michael, if you want to take the reins here.
Yeah, all right, can you hear me?
Sounds good.
Great. So did you know that dinosaurs are actually a major inspiration for airplane wings? That's right. So as I've discussed previously, I'm not going to talk too much about it today, the particulars of it, but birds are a group of living dinosaurs. And when people were making the first flying machines, we studied closely how birds fly and how they are able to turn and maneuver throughout the air. If you look at the cross section of a bird wing and an airplane wing, these cross sections are called airfoils, by the way, you can see that they're pretty similar shapes. So for a quick physics lesson, the top part of the wing is concave, it's arched, or convex, it's arched. So that the air, when you move it through the air at a high velocity, the air on top flows over it more quickly than under the bottom, which causes lower pressure up above the wing and higher pressure of air below the wing, which allows for lift. And so both planes and birds wings operate, in the same basic way. And further, when the Wright brothers were designing their gliders back in the early 1900s, they noticed how pigeons and other birds are able to change the orientation of their feathers during flight, thus changing the shape of the wing to be able to bank and make turns in midair. And so the Wright brothers made their wings out of a cloth that they could morph and warp during flight to allow for the wing to change shape, thus helping steer their aircraft. Now, if you've ever been on an airplane or next time you're flying, notice how the wing isn't just like a single hunk of aluminum. There are several panels and edges that are movable. The pilots can control to change the shape of the wing so they're able to maneuver the aircraft more readily. And we've studied more than just the wings of birds for inspirations for biomimicry. So some of the newer Japanese bullet trains are modeled after the beak of a kingfisher, and this minimizes air resistance, which allows for increased speed, better stability, and better fuel efficiency. And plus the passengers are essentially riding around in a giant model of bird beak, which is kind of cool in my opinion. As far as inspirations for biomimicry go, the fossil record is kind of an untapped reservoir. There are a lot of flight plans that are overlooked simply because we don't see them today on living animals. Take Microraptor, for example. Microraptor was a small dromaeosaur, which are the dinosaurs related to Velociraptor and kin. But this guy was very small, about the size of a crow. And like modern birds, Microraptor was covered in asymmetrical feathers that were the perfect shape to slice right through the air. They're called flight feathers. And so Microraptor was covered in these feathers. So modern birds only have them on the arms, right? They have 2 wings. But Microraptor had these flight feathers on the front limbs and the hind limbs. So this was actually a 4-winged dinosaur. And the tail would have also been covered in these big feathers too, which would almost provide a 5th wing. And there have been a few papers that kind of model how this thing would have flown. It wouldn't have done powered flight like a modern bird, but it would have done more of a gliding thing from tree to tree. And speaking of flying, pterosaurs are also an overlooked model for flying machines. So pterosaurs were a diverse group of flying reptiles, not dinosaurs. I cannot emphasize enough that these aren't dinosaurs, but they were flying reptiles that include the largest animals ever to fly. I mean, some of these the biggest ones got close to 40-foot wingspans, and that just blows the biggest bird out of the water. These things could get absolutely massive. And so, we have to figure out, how did they do that? How could they get so big and still fly? So there are 3 groups of vertebrates that are able to fly, and each of these groups has a different way of solving the problem, how do I fly? So birds, of course, most of their wing surface is covered in feathers, which is a highly controllable and adaptable surface that they can change the shape to do different things. Bats have a pretty thin, simple membrane stretching between their fingers, and pterosaurs are often compared to bats, but they're very different. So they do have a membrane, but the membrane is, they have a single membrane that stretches from the tip of one finger and connects to the body. And this membrane is very complex and thick. It has multiple layers. So these, they provide there's so many alternatives to solving some modern problems in the fossil record that most people overlook. Now, one of the drawbacks to looking at extinct species to design things like aircraft is also the main reason that it's so overlooked as a source of inspiration for biomimicry. Fossils are rare in general. We almost never get complete skeletons, and it's even more rare to find soft tissue, which is where a lot of these biology-inspired designs come from. But we do have data, and we are constantly getting a better understanding of how these animals flew. And in the case of pterosaurs and Microraptor, we have a very good idea of how they flew. And there are even more species of some flying dinosaurs that provide even more ideas for new aircraft and wing types, and show that truly unique and, more importantly, unpredicted combinations of flying features. First making airplanes, and this isn't, I haven't looked too deep in the history of this, but just kind of, if you were one of the first people trying to design a flying machine, it makes sense, with what we've talked about today. You look at how nature has already solved the problem for you. You don't have to start from ground zero, because that's just essentially a waste of time. But birds have been doing it for millions of years. So seems like they have it figured out pretty well. So let's see how they do it. And that's how it goes.
I just wonder, if a classroom were to list and research, list a lot of things, products in their classroom or things they have in their home that would tie into some kind of biomimicry,
Mm-hmm.
Yeah.
A surprising amount of our inventions are, we got it from looking at nature.
Mm-hmm. And that's what inspired this whole topic, right, Emily? Because Dr. Carter sent that STEM article, and it was a scientist in Western University, I think it was, and studying about the lotus plant And oh yeah, and then how the water just rolls off of the leaf when it's in the pond. Like,
Right.
how does
So much of hydrophobic materials, like anything like that. Yeah, I mean, even Velcro was originally designed as inspired by the way that plants are obnoxiously sticky with their seeds because it's a good dispersal method. To spread their seeds further if it gets stuck in an animal's fur, and so that kind of hook fastening system that Velcro uses was originally thought up by looking at the way that nature uses these sorts of things. So there's so much of that we don't really think about. We don't consider how much of what around us was originally inspired by natural processes and natural structures.
And that's one of the many reasons why we need to study nature and have a better relationship with creatures that are out there, because then we learn
So much.
more, not just
And
about them, but about ourselves.
I mean, we could go into an entire other conversation about pharmaceutical development. Is that's one of the reasons why they talk about biodiversity importance in the Amazon rainforest and in coral reefs especially, is that like all of these things that are in competition that are they have their own antimicrobial properties, they have their own venom properties, and just being able to understand better why these chemicals are used, whether it be a chemical or an actual structure. There's so many things that we can learn from nature to accomplish just about any task that we need to.
Well, is there anything else to add between Michael and Daniel? Because if not, we can just wind this up here. I appreciate your PowerPoint presentations, and I don't think Dr. Gonzalez is with us anymore, but it would be nice to feature him sometime in the near future. I would like to learn more about manatees, so that's your alley there, Emily. Yeah. And Daniel, are you going to get that specific type of gecko sometime this year?
I mean, what gecko isn't on my list of worth getting, you know? No, I do plan on growing my reptile collection. You know, if anyone is worth talking about, I believe Michael went from like 0 to 20 in like a week. So
it was 0 to 10 in a few months, like less than a year. Like, I wish it was 20.
He's got the lovely geckos, but they're not the kind of geckos with those sticky feet.
Speak of the devil, Emily over here with all her ball pythons and rosy bows too. Yeah, I'm like the coronavirus, but of reptiles. If you hang out with me, you're bound to get a reptile. It's gonna.
You really are, yeah.
You really are
contagious.
But no, I definitely do plan on getting that species again. My biggest goal, I have 2 species that are on the top of my list. Well, 3, 4, 5. Shoot, I have a lot. The Philippine sailfin dragon. Oh my goodness!
Good luck with that
Jesus. Satanic leaf-tailed geckos. I would love to get some Europlata species again. Brookesia, which is the pygmy chameleon, and the all-time one of my life is Draco volans, is the flying lizard. If I could get that, it'd be over. But
okay, so what have we not talked about? Because if we don't have Dr. Gonzalez next week, we might need to feature the other creatures that you have not featured in Personal Pet series.
I don't think we've done any of the beaded lizard. I still have species of rattlesnakes. I think we can go over.
Okay.
Okay. And then I have tons of friends. They have all sorts of different species that we can work together. So however and whatever we need, or whatever you guys, our viewers, would like to see, please leave us comments, send us a message, send us an email, talk to us. If you're a teacher, send us an email. We'd love to work with you and your students. If there's something you guys are going through in biology, I'm telling you, if it has to do anything with paleontology, my guy Michael over here, or anything, in all honesty, anything at all, Emily's got you, but she loves her marine biology. And Charity is just so much fun. She knows how to bring in a lot of fun and energy to any activity that you guys need. Me, I'm just a crazy guy. So whatever y'all need, we got you.
Okay, thank you everyone for joining us.
It's
Thank you.